Hi, this is my diagram of the resting membrane potential. Here we have is the plasma membrane of the neuron, which is slightly permeable, meaning it allows what goes inside of the cell and out of the cell. The plasma membrane has two sides, the extracellular fluid and intracellular fluid. The extracellular fluid is mostly composed of positive charge sodium ions, and the intracellular fluid has also positive charged potassium ions alongside with cellular proteins which are negative charge. The neuron uses sodium and potassium pumps, which makes sure that there's a higher concentration of sodium ions in the extracellular fluid and there's a higher concentration of potassium ions in the intracellular fluid to make sure there's balance in between the two fluids. At the same time, there's electrical potential here at the plasma membrane because the potassium ions, both sides are both positive, but the cellular proteins are negative, which cancels out mostly potassium charges, making it more negative than the sodium ions in the intracellular fluid. Next, the plasma membrane uses ATP to take sodium ions and put it into the cellular fluid, and it also uses ATP to take potassium ions and take it into the intracellular fluid, making a change in between. This allows to set up the resting membrane potential and allows the intracellular fluid to remain at a negative 70 MV or in a polarized state. Next here is my local potential diagram. Right here is a neuron. When dendrites receive a stimuli or chemical change, this signal can vary on its strength, meaning it can travel through the soma, onto the hillock, and through the whole neuron. That signal is called a local potential. Local potentials are graded, meaning they can vary in the strength of the stimuli. If local potential's signal is strong, it can cause nearby sodium gates to open up, which allow a huge intake of positive sodium ions to enter and diffuse into the intracellular fluid. And this diffusion causes the intracellular fluid to become more positive than negative. And this change creates a disturbance of the resting membrane potential, causing the membrane to become depolarized. Hi, this is my action potential diagram. This is a membrane pictured in a polarized state and has a value of negative 70 MV. The gates are closed at this time, and it's in a rest and ready state, meaning when a local potential is met for an action potential to begin, the signal is to be strong enough to open the sodium gates. When local potential opens the sodium gates, we reach a value of negative 55. That's close enough to start an action potential. When the gates open and the sodium ions start to pour out into the ICF, making it more positive, that's when the polarized state is disturbed because of the positive charges. That's when depolarization begins. When that begins, we reach a new value, which is positive 35 MV, which is the peak of action potential. Action potential is reversible. Once it happens, it cannot be stopped. In this diagram, this pictures the sodium gates closing and the potassium gates to open, which allows potassium ions to quickly diffuse out into the ICF. This causes the membrane to go in to stop depolarization, and that's when repolarization begins, which shifts the positive value back into a negative value. When the value reaches negative 70 MV, again, the potassium gates close, and this pictures both gates are closed. And sodium potassium pumps are able to return the charged particles back to the original location, which allow the membranes to recover until that process happens again.